Okay, we're gonna review all of our natural disasters learning. I'm gonna go over the stuff you need to know, the stuff that might pop up on the final next week. So you can take any notes you want to. You could even use this video to help you on the final. It's not gonna be a test, it's gonna be like a little mini project. I think you guys will like it a lot more than a final, but we'll go over that more later. But this video is going to give you everything you need to know about the natural disaster stuff we've been doing. So if you haven't done your natural disasters notes yet, this is your lucky day because this will have a lot of the answers for you all in one video and you can get those turned in and get your points. So we're going to start with earthquakes. Earthquakes are just a shaking of the earth when tectonic plates move very quickly and suddenly, and that releases a lot of energy, which shakes the earth. So it's very much like kind of bending a stick slowly until it breaks. You can see that over here on the right, that you start with the stick and you bend it slowly like this, so it starts to bend and build up energy. You can see it's storing energy until it breaks, and when that breaks you can see it's like shaking back and forth very quickly. That's why it's kind of like looking a little blurry there. It's trying to show motion, so it's like shaking back and forth, and that's the releasing of energy. And that's like the earthquake portion here. So what happens is you have a fault line. I'm kind of bummed we don't get to watch San Andreas because it actually shows this pretty decently. If you ever get the chance to watch that movie, there's a fair amount of good earthquake and tsunami physics in there, and a fair amount of bad physics too. That was actually the project we were going to do, is to see what was good and what was bad about the movie. But anyway, you can see the fault line I drew there in the tectonic plates. So that's a place where two tectonic plates meet, either a convergent or divergent or transform boundary. In this case, it's a transform boundary because you can see they're moving side to side. One's kind of moving up here and one's moving down here. And usually that moves very, very slowly. As we saw, it moves like a couple millimeters every year. Most plates, maybe like 10 millimeters, which is like a centimeter. You know, the whole continent moves a centimeter. So you're not really going to notice that. But an earthquake is when it moves a lot faster, a lot more suddenly. So what happens is that tectonic plates, here it's not perfectly smooth, right? It's kind of rigid. So there's bumps and cracks and snags and things like that along it. You can see I'm kind of trying to demonstrate that with the pen tool there. It's not a perfect fit. And so as the left plate moves up to the north and the right plate moves down to the south here, they catch and snag on each other and it builds up energy. And that's that buildup of energy stage right here. As it starts to build up a lot of energy because those plates get snagged on each other. And it can't hold infinite energy, right? The continents keep moving. It's not going to stop because it hit a snag somewhere. And so eventually the parts of the plates that are kind of stuck on each other, that are caught on each other, will just break off. Just like anything, when you force it too much, it'll break. Same thing with the Earth, with the tectonic plates. So that's the stage 3 right here, the slippage, is when the piece that was kind of caught, stuck between the two plates breaks. It releases all of that energy, and the plates slide very quickly and very suddenly, and that's the earthquake. And then it's slow. The Earth settles back down here into a new resting position, and sometimes that can take a couple tries. Sometimes it'll hit a resting position that's not very stable, and it can shift again. So that can cause aftershocks or even secondary earthquakes. Sometimes if it's a very severe secondary release of energy, but eventually, the Earth settles down and all of the snags break and it's able to move at its usual, 1 centimeter a year or whatever. So that's an earthquake. Basically, what happens is builds up a lot of energy. A piece or several pieces kind of break, snap, and it releases all of that energy in one violent shake. Here's the key terminology. I'm not going to go too much into it because you could just pause the video and copy down the definitions. A couple things to note: the epicenter is on the surface. That's the land that above the part of the Earth that actually breaks. So when I was talking about the break on the last slide, that's like the focus here, where the two pieces of the Earth, the two tectonic plates get kind of stuck on each other. They get snagged and then they break. That's the focus, and that happens underground. So the focus, the actual break of the Earth would happen like right here. Let's highlight that right there, underground, and the epicenter is directly above that. So you may hear in the news the epicenter of the earthquake was near San Francisco or something like that. That means that the part of the Earth that actually broke, the cause of the earthquake, is pretty much directly underneath San Francisco, and that would cause a very powerful earthquake. Generally, the most powerful shaking is at the epicenter. And finally, we have what's called the Richter scale here. It's a log scale. I would go more into this if I was actually, in the classroom able to support you, but it's a different way of graphing numbers, basically. And so what a log scale is it means every time you increase by 1, something gets 10 times stronger. So going from like a 2 to a 3 means it's gotten 10 times stronger. You can see, let's go with the examples we have here, right? So if we go from a 5 to a 6, it's 10 times stronger because we went up by 1. If we go from a 5 to a 7, that would actually be 100 times stronger because 5 to 6 is times 10, and then 6 to 7 is times 10 again. So that's 10 times 10, so 100 times stronger. Then if we go up by 3, right, 5 to 8, that's 1,000 times stronger because we multiplied by 10 again. So every time you increase by 1, it gets 10 times stronger. So you can see here a magnitude 2 is not even noticed, right? We don't even see that. Maybe you might barely notice it. And then let's look here at magnitude 4. Or let's look at a different one. Let's look here at like magnitude 8. Magnitude 8 is like total destruction of cities, total damage. So it looks like we only got 4 times stronger, right? We went from 2 to 8. 2 times 4 is 8. So it seems pretty drastic, right? I should get the Ron Burgundy meme. Like that escalated quickly. We went from 2 to 8, and all of a sudden we went from not even feeling it to destroying the city. But remember, each one of these, each time we went up by 1, it's actually times 10. So it was times 10 again, which is times 100, times 10 again, which is 1,000, then another times 10, so 10,000, another times 10, 100,000, and then finally one last one, a million times stronger. A magnitude 8 earthquake is 1,000,000 times stronger than a magnitude 2 earthquake. So it looks like 4 times because that's how we're used to it, right? 2 times 4 is 8, not in a log scale. Here, log scale. In the log scale, 2 times 1,000,000 is 8. And it's interesting why. It has to do with graphing. It makes your numbers fit on graphs better. That's generally why you would do a log scale. That's the primary reason. So when you progress into college level math and stuff, you might see more of that, but I wanted to introduce that to you here. But all you need to know is that every time you go up by 1, you actually multiply times 10. So that's the trick with the log scale, and that's called the Richter scale for earthquakes. So if you ever hear a Richter scale 6, something like that on the news, that's what they're talking about. They're talking about how strong the earthquake was. Okay, we spent a lot of time there on earthquakes, but earthquakes are probably the most likely thing to come up in maybe a test you may have in the future, like the CMAS or something like that. So I wanted to cover that fairly thoroughly. The rest of these natural disasters, I promise, won't take nearly as much of your time. So if you want to copy these definitions down, just pause the video. That's the great thing about YouTube. You can take as long as you need to copy the information down. The one thing I do want to go over here is the wave shoaling. Wave shoaling is this phenomenon where you can see most of the time in the ocean here, when the wave is out in the ocean, all of that energy from the wave is able to just make these kind of nice, big, long waves because it has a lot of space to work with. As the wave gets approaching the shore here, it runs out of space, right? If the wave wanted to come on down here, it hits the ground. Well, the water wave can't really penetrate into the ground, so it kind of gets forced up. The whole situation just gets forced up by the ground, by the shore. So usually, right? Usually you just have nice small little waves that come in there, and it's not really a big deal. Like they get forced up maybe a few inches as they approach the shore, and it makes for good surfing sometime. With a tsunami, there's a lot more energy. This wave is taking up quite a bit more space, but it's not an amount of space that's super noticeable even out in the ocean. You could be out on a cruise ship out in the open ocean. A tsunami wave could pass right through. You might not even know. It might be a slightly bumpy minute or so, but it wouldn't even really be noticeable compared to just your general wind-caused waves out there. It's when it gets close to the shore and the shore forces this big wave of energy to have nowhere to go but up, that you get this tsunami, this tidal wave that kind of creeps up out of nowhere almost, and then comes crashing down onto the beach with huge devastating force. So that's where this term harbor wave comes from. A harbor is like where all the boats are stationed and stuff like that. It's basically a beach. And so you don't see this wave until it's basically almost in the harbor. So it appears to pop up like a sea monster almost and swallow the harbor, swallow all the boats and everything, and that's why the Japanese called it that. So tsunami means harbor wave, and that the wave shoaling, it's because the ground here pushes everything up as the wave of energy approaches the shore. In terms of some historical information here, back in 2004, most of you guys were probably not even born yet, to be honest, or very, very young. But there was a huge tsunami in the Indian Ocean that hit. It was so huge, it hit multiple countries. So if you could picture an ocean wave that big, it was generated by an undersea earthquake, and just a huge amount of devastation. Probably communities still recovering from this one, to be honest. In the video, we also saw a way back historical reference to a tsunami where the Greeks thought the god Poseidon had saved them. So that's a more interesting historical one. The Indian Ocean tsunami really is a devastating and horrible event. And so the early warning one, if the low part of the wave happens to hit shore first, which happens about 50% of the time, like it's a 50-50 shot, either the high part or the low part of the wave is going to hit first. If the trough hits first, you'll see a very weird kind of pulling out it would be like a very, very, very low tide, even lower than low tide. So if the beach starts to grow and it looks like the water is retreating very strangely, that can be an actual warning sign of a tsunami. which again is one of the key moments in the movie San Andreas that we would have watched. So if you ever watch that, check out that and pay attention to that scene. But that can definitely be a warning sign of a tsunami. So let's move on to flash floods. Flash flood is the first natural disaster I had experience in Fort Collins. I think I want to say 1997, something like that. There was a big flood, but it's just a big pouring of rain that overwhelms the Earth's ability to handle it. So the Earth has its own drainage systems, rivers and streams and stuff. When it rains, the water eventually makes its way into one of those and finds its way back to the ocean. But sometimes it can rain too much in one spot and it overwhelms the rivers, and the rivers can overflow, which can wipe out buildings and anything near the river. The ground can also get waterlogged. It can get saturated with too much water, and that can cause problems with infrastructure as well. So it's just too much water too fast. The Earth can handle water, but it has a limit on the speed at which it can handle water. So if it gets hit with water too fast in one spot, that can really overwhelm things. An example is the 1972 Black Hills flood in South Dakota, where, again, a big community, Rapid City, South Dakota, is on a river. And so there was a huge rainstorm. It rained very, very quickly for a long period of time, and that river just got overwhelmed and flooded very quickly. And it caused a lot of damage and a lot of fatalities. And that's just some of the people underestimate how strong of a force water is. Water is very heavy, and it can really carry a lot of power with it if a whole river starts to overflow. So on the how to prepare side, again, just go ahead and pause the video, but it's pretty straightforward. The higher you are, the better for when it comes to flood safety. The three types of flood, we just talked about the river flood, so I won't go over that again. Coastal flood is same as a river flood, but instead of a river, it's a coast of some kind, a very, very large lake potentially, or ocean, something like that. A hurricane or a tsunami could actually cause a coastal flood. So in addition to, the horrible hurricane you're dealing with, you also now have a flood too. So that's just a double whammy there. And then an urban flood is one where, like I said, the ground can actually soak up quite a bit of water, but not concrete. We're talking about actual dirt ground. So if we get an area that has too much artificial ground, concrete, things like that can't really soak up water, then it's much easier for a rainstorm to overwhelm a city's drainage ability and cause what's called an urban flood, like you see in this photo here, where the water just has nowhere to go. And so places with a lot of open space, a lot of grass, dirt, natural ground, they tend to be less prone to this urban flooding because there's more area for the ground to absorb water. All right, let's take a quick look at wildfires now. We're moving along faster now. Again, these definitions, just pause the video and copy them down if you want to. Another important thing is that in nature, lightning is a cause of wildfires and can definitely start a wildfire. Lightning bolts have a huge amount of energy contained in them and can definitely light a tree on fire. However, most wildfires are started by humans. I think the percentage was 76%, but I don't remember exactly, but it's something very close to that. So it's about somewhere around 3/4 of all wildfires, when they found a definite cause, it's been shown to be like a cigarette butt or a campfire or arson. Someone did it on purpose, something like that. So you want to be very careful when you have a fire of any kind that it gets put out properly and safely. Weather is an important factor in fighting wildfires. So if it's very dry, then obviously the plants are going to be very dry as well and easier to light on fire. Wind can also pick up those embers that you saw on the last page. Embers are basically just little burning bits that are light enough to be carried away by wind. So wind can pick up those embers and carry them sometimes for over a mile, actually, and start new fires, new hot spots that make it much harder to fight, because now all of a sudden there's a second fire that you have to turn around and fight somewhere else. Even if it's close by, that still makes it a lot more challenging. An example of that being the Black Forest fire in Colorado Springs in 2013. A huge fire. Fortunately, only 2 deaths. That's a pretty low number, honestly, for how widespread and how devastating those fires were. So I remember just hearing in the news reports that summer how many secondary fires kept sparking up from the embers of that fire because it was so windy as well. So that's just an example of how the wrong conditions can make fire even more dangerous. 84%. Okay, there's the exact number. Sorry, I think I said 76% earlier. It's even more than that. 84% of wildfires are started by people, not lightning. So that means only 16% is started by lightning. So that's why Smokey the Bear, he's like the mascot for forest fire prevention, and his slogan is "Only you can prevent forest fires," because it's up to humans to make sure they use fire correctly. So 3 tips: don't leave a fire unattended. Matches or anything like that, don't just toss them on the ground. Make sure you dispose of them properly. And if it's windy, probably not a good time to start a fire at all. Okay, let's move on to tornadoes. Again, the basic definitions, you can just pause the video and copy down. Basically, tornadoes are caused by giant thunderstorms called supercells, and you get a mixture of warm, humid air mixing with cold, dry air, and it creates this funnel effect where the warm air goes up while the cold air comes down. And it's a very unique situation that tends to really only happen in the United States. Most tornadoes in the history of the world have happened in the United States because we have this perfect combination of cold air coming from the Rocky Mountains. So the Rocky Mountains kind of block off the warm ocean air from the Pacific and creates a nice stream of cold air coming over the country. And then the Gulf of Mexico is a source of nice, warm, humid air. So you get that perfect mixture in the middle of the country. And Aurora's just on the edge of that. So we don't get too many tornadoes, very rarely, but it does happen. But over in Kansas, where Wizard of Oz happened, tornadoes happen quite frequently because of that Rocky Mountain air mixing with Gulf of Mexico air that just has that perfect funnel effect. So for tornado safety, most places, including Aurora and other eastern parts of Colorado, will have tornado sirens. And you may have heard them before, even if it was just a test, or maybe even once or twice for actual warning. But if a tornado is spotted, the city will activate the tornado sirens, and that'll just let you know to get in the lowest part of a building. If you can, a basement is great. If not, just make sure you stay away from any outside windows, because the wind can break those windows, and then the broken glass is very dangerous. An example of a tornado is the one pictured there, and I picked that one because it's a tornado that I basically drove through on accident. Obviously not through the actual tornado, but it basically looked like this out of my car window. That picture looks exactly like how I remember this event happening. I didn't take that picture, but I might as well have. So it it was a crazy experience and not one I want to go through again. And it caused a huge amount of damage. And again, because of the warning system, only one death. People were able to get into the basement, into the safest parts of their houses. So that was fortunate. I remember at the time there were numerous people missing, and the news reports just over the course of the next several hours and probably over the next couple days, to be honest, they kept having reports of finding people who were missing. So those are actually great news reports. And then by the end, there was only one person who didn't make it out. So that was actually good to see that it was just property destroyed, not too many lives. So thunderstorms here are probably my personal favorite just because the physics involved. I think, it's very fascinating. So I'll again let you pause the video to get the definitions if you want to. But basically, electricity really likes metal. So if thunderstorms are around, stay away from metal things and stay away from tall things because the electricity, it wants the easiest pathway it can get to the ground. Its goal is to get to the ground, so it's going to latch on to the tallest thing around, and you do not want that to be your body. Trees get struck by lightning quite frequently because of this, as well as large metal power poles and things like that. And so most things like that have built-in ways to deal with electricity. However, if a tree is old and dried out, it's not as resilient, and so an older dried out tree getting struck by lightning does tend to burst into flames, and hence how lightning can be a cause of wildfires too. So a lot of these natural disasters go together as well. We saw floods and hurricanes and tsunamis all kind of going together. Lightning can cause thunderstorms, or well, obviously lightning can cause wildfires. Thunderstorms can cause tornadoes. So a lot of these things go together, which kind of stinks because one natural disaster is usually difficult enough to deal with, but they like to come in bunches. So here's my favorite part. It's the physics of it. So it's like static electricity on your carpet. I'm sure you felt on a carpet before wearing socks or something where you build up that electric charge, then you touch the door handle and the door handle zaps you. This is the exact same thing almost, just on a huge scale. It's like a static electricity zap that goes from the sky to the ground, or many cases in the sky as well. It stays in the sky going from cloud to cloud, but it can also, as we are well aware, it can go down to the ground too. So what happens is clouds are formed, and clouds are made out of water, like this, and water is made out of atoms of hydrogen and oxygen, and those atoms have positive pieces called protons and negative pieces called electrons. And as all of those water particles rub together, they can trade electrons sometimes. Electrons can bounce from molecule to molecule and from atom to atom. And so the negative ones that gain electrons, say a water molecule steals an electron from its neighbor, it's going to become negative, and it's going to come join its negative crew down here in the bottom. And the ones that lose their electrons are going to go up to the top here with the positive layer. So that keeps happening, and eventually enough of that charge gets built up that it's actually able to join to find some positive charge friends on the ground and link up. And that's when that lightning bolt occurs, is when enough charge builds up that it's able to basically turn the air into a little wire, is essentially what happens, and that electricity is able to flow through the air to the ground and escape. Because electricity really likes being in the ground. That's essentially what happens there, is it's trapped in the cloud until it's able to build up enough electrical power to connect to the ground and escape the cloud and zap into the ground. So we've outlined that here in this 4-step process for like the 4 steps four steps for forming lightning, basically. So you've got the cloud, the particles in the cloud rub together, just like your shoes or socks on a carpet rubs on the carpet to build up charge. You get the positive layer on top and the negative layer on bottom, and it keeps building up what's called a voltage. That's the electric power, basically. The amount of electric force that gets built up here is based on the voltage. So it keeps building up more and more and more voltage until it's actually able to shoot through the air and into the ground. And that's when you get that lightning bolt. Hurricanes are another very common thing we deal with here in the United States, but fortunately not anywhere near Colorado. Fortunately for us, I guess. I'm sure Miss Myers has a lot of experience with hurricanes from her time in Florida. But essentially, hurricanes are physically very, very similar to tornadoes, just much bigger. They're like tornadoes, but the size of entire cities. But because of that, the power and energy gets more spread out, so they tend to have not as powerful winds, but they also happen over water. So replace that devastating super-powered wind, even though these can get up to tornado force winds as well. The worst hurricanes can, and they'll wipe out whole cities. But most hurricanes, the primary damage comes from the water, either coastal flooding, urban flooding, or just something called a storm surge, which we'll go over on the next slide. So pause the video if you want to write down any of these definitions. But again, the cause of the hurricane, same as a tornado. You get warm ocean air that mixes with cold air on top. And actually, I really, really like this picture. This picture would work very similarly for a tornado as well. You get the cold air coming down through the center here. That's the blue arrows in the picture. So I'll go ahead and erase my arrows here. And the warm air kind of spirals around it. It does like this dance here. And that's where that spiral pattern comes from, is the warm air spiraling its way up. Then it gets to the top and cools off, and it can shoot back down here. And you get these patterns, just like that, of the hot air moving up, cold air moving down, always in a spiraling circle. So that's where we get hurricanes, and it's the same thing for tornadoes. So again, most damage from a hurricane comes from the water. A storm surge is very similar to a tsunami, generally not as tall, but can be equally as powerful. A very commonly referred to example is Hurricane Katrina. The storm surge overwhelmed the barriers that protected the city of New Orleans and flooded the whole city, essentially. Took a long time to recover from that one. Many people never moved back or weren't able to get out in the first place. And so that was one of the most devastating natural disasters, certainly to occur in the United States, but worldwide as well. So here's one that there's been a lot of these we talked about, tsunamis, hurricanes, things that could never happen in Colorado. Here's one that happens all the time in Colorado. It's the blizzard and avalanche. So I'll let you pause and copy down these definitions. But basically, a blizzard is caused in the same way as a thunderstorm or a tornado or hurricane. It's always caused by a mixing of warm and cold air. That's what causes so many of these storms. It just depends on how and where the warm and cold air mix that it determines which type of these storms it is. So obviously blizzards are when it happens in the winter in a very cold place. So the cold air and warm air mix, but the cold air ends up kind of dominating the process. And so any of that rain and stuff is turned into snow, and snow doesn't electrically charge nearly as easily as a typical like cloud particle would, which is why we tend to not see lightning in a blizzard, is because the particles don't share their electric charges. The electrons don't pass as easily in the cold weather environment as they do in the summertime. So I have actually been on a ski mountain in a thunderstorm before. It was terrifying and I don't recommend it. But fortunately, most of the time, winter, you are not going to encounter lightning, because even though it's the same thing, you're still having that warm air mixing with the cold air, and that's what causes all of these storms. It's too cold for that electricity portion of it to really occur. Avalanches, on the other hand, what causes those are patterns generally. So you get a lot of snow and then a lot of sun, which melts the top of that snow and then, freezes at nighttime. And so you get like a layer of ice, and then the next day it'll snow more on top of that ice. And then the top layer of that new snow will melt a little bit and freeze overnight, and you get another ice layer. And you just get these layers of snow and ice, and eventually it gets really, really heavy. And ice is pretty slippery. And so one of the bottom layers of snow and ice will start to slip. And when the bottom layer slips, anything on top of it slips too. And the whole ice snow layer cake, whatever you want to call it, falls off the mountain, is basically what happens. So that's where an avalanche comes from, is you get these patterns of snow and then warm and then cold and then snow and then warm and then cold, and you just get these layers of snow and ice until it's too heavy and it breaks. And so actually, if a lot of people who do backcountry skiing and stuff are trained so they can dig into the snow a little bit and see, and if they see any layers like that, they know we're not going to ski here because the avalanche danger is too high. So the zones of an avalanche, you get the fracture zone up top here, where the initial break happens. That's where the slide begins, where the top layers start to slide off the bottom layer. Then everything generally gets funneled into a pathway, because mountains typically have, bumps and ridges and stuff, and so it'll find kind of a pathway like that, and then it'll split out. Deposit means to drop off or leave behind. So that's the deposition zone, where all of the snow, ice, trees, rocks, whatever that gets caught in the avalanche gets spit out at the end in the deposition zone. So to prepare for an avalanche, one, if you're going anywhere that's not in a ski area, you want to have an avalanche beeper, which is tied to GPS, and you want to make sure somebody knows where you're going, so if you don't come back in time or something like that. Honestly, you're at that point you're too late if you're in an avalanche. So it's generally you can send an emergency distress, or somebody else you're with is free and able to get help. But that avalanche beeper is your best friend because it can lead a rescue team right to you. So why is it so safe in a ski area? Well, it's because ski areas and highway patrols, places where there's a lot of people who aren't necessarily avalanche trained, those places will use C4 in order to bomb areas where avalanches might form in order to keep them from layering up. So as soon as it gets a couple layers on it, they'll go and bomb it and intentionally start a very small avalanche in order to prevent larger avalanches from building up. And so they keep any ski area or highway or anything like that very safe because they can schedule basically when they're going to have an avalanche because they have the bombs. Preparing for a blizzard, again, probably already know this because, well, we live here, but you want to make sure you have blankets in your cars and canned food and bottled water because you never know when in the winter. We can be pretty sure it's not going to happen in June, but in the winter you might not be able to open your door because there's 4 feet of snow trapping you in. So you always want to make sure you're prepared for that when you live in a place like Colorado. So that was a lot of information here in 42 minutes, but I hope you found it useful. And again, you can revisit this video to help you with our final, which won't really be an exam, but sort of like a little mini project, and it will have a part about natural disasters on it. And everything you need to know to do that was in this video, and also in all of the work you've been doing the last couple weeks. So now you should hopefully be prepared for anything you see next week on the final, and a little more prepared to go out into the world once we're allowed to again, and maybe face some of these other natural disasters that hopefully I don't hope you find these natural disasters, but if you do, you'll know a little bit more about what they are and how to prepare and stay safe from them. So that's all for today. Make sure you fill out your exit ticket to get your points for today, and that's it for Earth Science for a semester. We're moving into review mode now, so hopefully you guys feel like you've learned quite a bit.